Materials are what we call ferromagnetic. And two examples, the two most important examples, are iron and nickel. Okay, they're ferromagnetic materials. And it turns out it's the electrons that's crucial. Electrons have very strong magnetic moments associated with them. But mostly, and you've seen this before, when you build up an atom, when you put electrons into different energy states in an atom, and you build them up, you've drawn pictures that look something like this. I have an energy level, and I have another energy level, and another energy level. And those correspond to different orbitals. And I stick one electron in like this, and one electron in like that. Then that's now a filled state. These correspond to electron with its magnetic moment oriented one way or oriented the other way. And mostly you do that. You fill them up with pairs, right? With spin one way, spin the other way. So the net result is I get no net magnetic moment for most materials because the spins are paired with each other. But there's certain materials where that doesn't happen. We tend to have these unpaired spins. And beyond that, these materials, the unpaired spins like to line up with each other. And so you end up having, like, the atoms themselves have very strong magnetic moment, and those magnetic moments like to line up. And so if one atom has this magnetic moment like this, the next one next to it likes to have a magnetic moment like that. And if you have a material like that, it produces something which is ferromagnetic. Now, here's what happens if you have a ferromagnetic material. If I imagine taking like a small piece of iron right here. Iron is ferromagnetic. And I look at a tiny piece of it. Magnetic moments in this way. Stick one atom, magnetic moment that way. The next atom comes down, magnetic moments this way. And I start building it up. I'm going to build it up with the magnetic moments all pointing in the same direction. But that's pretty highly not random. That's very, very orderly. And entropy doesn't work well with that. I mean, it's just not a good thing. And so what will happen is if you start piling up a whole bunch, you'll reach a point where it breaks down. And then you're going to build up another region where the magnetic moments are oriented differently. You build up a different domain. And so if you take a piece of iron and you look at it on a microscopic scale, it's extremely strongly magnetized on small scales. But the sample as a whole, if you just take a chunk of iron, is not going to be magnetized because they have all kinds of different domains, all of them which have net magnetic moments which point in different directions, no net magnetization. But the material can be magnetized. If you take this material and you put on a strong magnetic field by putting a permanent magnet near it, what happens is the domains which are favorably oriented will grow at the expense of the ones which are poorly oriented. So if I put on a big magnetic field that's going up, this domain grows, this domain grows, this one grows at the expense of the ones around it. And so I end up producing a net magnetic moment in the material. And if I do that with this material, this one grows, this one grows, this one grows. I get a magnetic moment that goes in this direction. In other words, I have a south pole at this end of the material. And I produce that by bringing in a magnet with the north pole at that end. Net result, what can you say about the force between those two things? Attractive. It's attractive force. So if I have a magnetic material and I bring a magnet near it, it's going to become magnetized. And it's going to become magnetized in a way that leads to an attractive force. Okay? I'll show you an example of this. This is a real strong magnet, and I have it in this pie pan. And I have these Canadian coins on the bottom of it. Canadian coins are made out of nickel. Canadian nickels, made out of nickel. U.S. nickels, not made out of nickel. We should rename them, honestly. I mean, that's one of my quests in life is to get the nickel renamed, because it's not made out of nickel. I mean, what's that about? But Canadian nickels are made out of nickel. And so they're magnetic. They're ferromagnetic. Yeah, Renee is going to help me out here. Thank you. That's going to make everything go a lot more smoothly. Oh, thank you so much. Here we go. We'll start with the one Canadian dollar coin. Excellent. Lines itself up like that. Here comes a quarter. Lines itself up like so. And again, it's north at the top. It's south on the bottom. North at the top, south on the bottom. The next one comes in. It gets magnetized. It works like a magnet. And it's going to line itself up. And then the next one comes in like so. But they're not actually touching the magnet directly. And it's actually the magnetic field of the magnet that makes it go. I can take this stack and I can pull it away from the plate. There's actually some airspace between there.